Hi there, this is A-level gravitation, and specifically we're going to be covering Newton's law of gravitation. So the objectives are to recall and explain Newton's law of gravitation, explanations in terms of Newton's law of gravitation in words, and then we're going to apply Newton's law of gravitation to physical problems. So when do we use Newton's law of gravitation? We use it when we have a radial gravitational field. So radial gravitational fields or radial gravitational fields act around point masses. Okay, so what we do is we assume that everything is just a point mass, an infinitesimally small point. So you might have a planet, but it acts as a point. The field lines, as you can see, all act towards the center, and they always act towards the center because gravity is obviously attractional. So Newton's law of gravitation from 1687, believe it or not. Newton proposed that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of their distance apart. So mathematically, the force is directly proportional to the product of the masses. So the force is directly proportional to the product of the masses. So that's m1, m2. And then inversely proportional to the square of the distance between them. So Newton's relationship was that the gravitational force is proportional to m1, m2 over r squared. Now, Newton didn't get the constant for this, which is the universal gravitational constant. That was done by Cavendish many years later. But essentially, the version of Newton's law that you'll be using is F equals g m1 m2 over r squared. Now this is a force, so it's a vector quantity. And g is 6.67 times 10 to the minus 11. And it's Newton meter square kg minus 2. That number's on your data sheet. So let's move on. Okay, let's have a go at this. Example 1. So pause the video and attempt it. Calculate the gravitational attraction force between bodies of mass 3 kilograms and 2 kilograms placed 50 centimeters apart. So it's a very simple application of Newton's law. So F is equal to G m1, m2 over distance squared. So G is 6.67 times 10 to the minus 11 multiplied by mass 1, which is 3, multiplied by 2, and then divided by the distance squared. Distance is 0.5 meters squared. So that gives us, so that's 1.6 times 10 to the minus 9 newtons. So as you can probably appreciate, the gravitational force that acts on a 3 and a 2 kilogram mass is exceptionally tiny, to the power of minus 9 newtons. So the gravitational attractive force for everyday objects that you might come across is significantly tiny. Gravity only becomes a substantial force when at least one of the masses is moon-sized. Okay, let's move on. I'll attempt this question. Remember that the gravitational force is a vector quantity, and in part A you need to do a couple of calculations, and part B is trickier, but I would advise that you try a diagram for both of these. So pause this video and attempt these questions, and then I'll show you how to do them. So let's do the first one. So we've got 0.2 and a 0.3. So we've got a 0.2 kilogram and a 0.3 kilogram. Separated by 0.15 meters. And we place the third particle 0.05 meters from the 0.3 kilogram mass. So like this. So that's 0.05 meters. and it's got a mass of 0.05, so 0.05 kilograms. So essentially we've got a gravitational force pulling in this direction to the right, and we've also got a gravitational force pulling in this direction. So we need to calculate both of them and then do the difference between them. So let's do the force due to the 0.3 kilogram mass. So we've got force is equal to G, which is 6.67 times 10 to the minus 11, multiplied by mass 1. So mass 1 is, we'll do 0.3, multiplied by the mass of the object, 0.05, and then divide them by the distance, square the distance, so 0.05 meters squared. So you put that in your calculator, that gives a force of, I'll just write this up here, 4.002 times 10 to the power minus 10 newtons. So it's a very small force. Then we've got the force to the left, so that will be the same calculation. So Newton's constant, so the gravitational constant 6.67 times 10 to the minus 11, multiplied by the mass, this time it's 0.2 kilograms, multiplied by the 0.05 kilogram mass, and then divided by the square of the distance. So the full distance is 0.15 meters, and we need to subtract the 0.05, which leaves us with 0.1 squared. So when we calculate that, we get 6.67 to the minus 11. I'm just going to write this here, but then I'm going to delete this working out, times 10 to the minus 11. Hopefully you followed that. So we've got two forces. So force at the top, 4.002 times 10 to the minus 10, and then a second force, 6.67 times 10 to the minus 11. So I'm just going to write these down. Two times 10 to the minus 10 newtons, and then the other force, which is 6.67 times 10 to the minus 11. Now what we should do with these two forces is just subtract them, and that will give us the resultant force. So these are the components and we need the resultant. So the difference between them gives 3.34 times 10 to the minus 10 newtons. So that's the resultant gravitational force that's acting on the third particle. So part B, where along the line it should be placed for no gravitational force to be exerted on it. So on this one we've got 0.2 kilogram on this side, 0.3. I'll make the diagrams a bit smaller. The full distance between it is 0.15 meters. We're going to figure out the distance to some neutral point. So we'll do the distance from the 0.2 kilogram mass, we'll call that R. And then this distance here would be 0.15 minus R. I'm just going to write this underneath, 0.15 minus R. At this point where the gravitational force will equal 0, this drawing is obviously not to scale. But the force that's moving this way would be equal to the force that's pulling it to the left. So I can say that the gravitational force 1 would be equal to the gravitational force that's pulling in the opposite direction. So what we can do in this situation is write the gravitational force, which is G M1, which is 0.2, multiplied by the mass that we're going to put at that point, which I'm just going to call M3 at the moment. So it's G 0.2, so mass 1 times the smaller mass divided by the distance between them squared. Now the distance is R squared, and that will be equal to the force that's pulling in the opposite direction. So that would be G, the mass, which is the 0.3, times the mass that we put at the point itself, so we'll call that M3, divided by, and this time the distance is 0.15 minus r, all squared. And as you can probably see that the g's will cancel and the mass of the object that's placed on the line will also cancel. So what we're left with is 0.2 over r squared equals 0.3 divided by 0.15 minus r, all squared. So if you want to have a go at that now, you can do. See if you can finish that off just to find r. I'm just going to make some space, so make sure you've got any notes down. So that was our ending point. So what we need to do is get all of the r's on one side. So 0.15 minus r all squared divided by r squared equals, and on the right hand side we've got 0.3 divided by 0.2. So that equals 1.5. And then on this left hand side what we can do is, well, first of all square root everything, because I don't want to deal with a quadratic. So the 1.5 we need to square root that. So we end up with, we can write 0.15 over r minus r over r, which is 1, equals the square root of 1.5. So the r over r is equal to 1. So if we take that and add it to the other side, what we end up with, therefore, we get 0.15 over r equals the square root of 1.5 plus r over r, which is 1, which gives us 2.22. Therefore, r will be equal to 0.15 divided by 2.22. So that gives us a distance of 0.067 meters. Now that's quite challenging, but if you finish that off, that's really good. Now let's move on. So there's some information here. There's G, which is 6.7. We can use the 6.67 that we have been using. We've got the mass of the Earth, the mass of the Moon. The R-Earth-Moon is the distance between the Earth and the Moon. We're going to need that in a moment. And the other one that we need is the radius of the Earth. Now this is on your data sheet, but it's 6.37 times 10 to the 6 meters. So if you want to have a go at question 1 and 2, just pause, and then I'll take you through the answers. So the first one, calculate the gravitational attraction force between two particles, each of mass 20 kilograms, placed 1 meter apart. So this is pretty straightforward. So force is equal to, so it's G m1 m2 divided by r squared. So the force is equal to G, which is 6.67 times 10 to the minus 11, multiplied by mass 1, which is 20, times mass 2, which is also 20, divided by 1 squared. That's 27 times 10 to the power minus 9 newtons. Question 2. So question 2, consider the Earth as a uniform sphere. Find the gravitational force on a mass of 5 kilograms placed on the surface of the Earth, assuming that the Earth can be replaced by a point mass, and then compare it with the weight. So the weight is really easy, so because weight is mg. So we're going to we'll do the calculation first and then check it. So we're going to do force is equal to G m1 m2 over r squared. So G is 6.67 times 10 to the minus 11, multiplied by the mass, which is 5 kilograms, and multiplied by the other mass, which is the Earth, which is 6 times 10 to the power 24 kilos. And then divided by the distance squared. So the radius of the Earth is 6.37 times 10 to the 6, and then square it. And that gives us 49.3 newtons. If we compare that with W equals mg, and we just do the mass multiplied by gravitational field strength, so 5 kilos times 9.81, that gives us 49.05 newtons. So basically the same answer. We could make this one more precise if we use a more precise version of G and also the mass of the Earth as well. Because the mass of the Earth is actually 5.98 times 10 to the 24 kilos. Let's have a look at the next two questions. So if you want to pause it, have a go at these. Question 4 is, well, the information is previous if you want to rewind if you didn't already write it. But question 4 is similar to the long-winded question that we did, the last example, the part 2 one. So if you want to pause that, thank you. So let's do a diagram. So we've got a 4 kilogram mass. 4 kilograms. And they are 80 centimeters apart, so 0.8 meters apart. And then there's an unknown mass, which we'll just call M. So 20 centimeters from the 4 kilogram mass, or 0.2 meters. The gravitational force is 0, so that's 0.2. So that distance there is obviously 0.6. And we know at this point, the neutral point, that the force due to the 4 kilogram mass is equal to the force from the unknown mass. So we've got G, M1, which is 4, so G times 4, times some imaginary mass that we put there. So I'll just call that M, divided by the distance squared, so 0.2 squared, is equal to G multiplied by mass, which is unknown M, times the small mass from earlier, divided by 0.6 squared. So the small masses cancel, G's cancel. Then it's just a case of rearranging to find M. So M is equal to 4 divided by 0.2 squared times 0.6 squared. And that gives us 36 kilograms. Hopefully that went okay. Right, we've got one more. Question 4. Considering the mass of the moon and the Earth and the distance between their centres, calculate at what point on the line joining their centres is there a net gravitational force of 0. So let's have a look at this one. So the sensible thing to do is to draw a diagram. So that's the Earth. And then some very large distance away we have the moon. The distance from point to point, centre to centre, is 3.8 times 10 to the 8 meters. And the Earth has a mass of 6 times 10 to the 24 meters. Meters, I mean kilograms. Definitely don't measure mass in meters. And the moon is 7.4 times 10 to the power 22 kilograms. And what we need is the point where the gravitational force is equal to 0. And that happens quite close to the moon. So that is the distance. We're going to look for this distance R. And then obviously the distance between the neutral point and the moon would be 3.8 times 10 to the 8. Subtract that distance R, so minus R. So now we've got a diagram. We can think about what's happening. So the gravitational force to the left by the moon, by the Earth, is equal to the gravitational force to the right from the moon. So I can write force from Earth is equal to the force from the moon. And then we just need to apply Newton's law of gravitation. So the force from the Earth is G, mass of the Earth. So I'll just put the numbers in, 10 times 10 to the 24, times some small mass that we put at that point, so I'll just call that M, divided by the distance, which is R squared, is equal to G again, multiplied by the mass, which is the mass of the moon, which is 7.4 times 10 to the 22, multiplied by some small mass, divided by 3.8 times 10 to the 8 minus R, all squared. So it looks a bit messy, but we can get rid of the G's, we can get rid of the mass M, and we've got the mass of the Earth divided by R squared equals the mass of the moon divided by 3.8 times 10 to the 8 minus R, all squared. So I'm going to have to clear the screen, so I'll make sure this is written down. and then we're going to move all of the r's onto one side, onto the left, and the numbers onto the right. Then we're going to square root as well. Just like this. So what we can do is square root both sides to eliminate the possibility of getting a quadratic. So we end up with 3.8 times 10 to the 8 minus r divided by r equals the square root of the mass of the moon divided by the mass of the earth. And that is 0.111. Then we just need to tidy it up. So just put an 8 there. So 3.8 times 10 to the 8 over r minus r over r, which is 1, equals 0.111. So rearranging that, therefore, we get 3.8 times 10 to the 8 divided by r equals 1.111. Therefore, r is going to be 3.8 times 10 to the 8 divided by 1.111. So calculating that, we get the distance from the Earth to the neutral point is 3.4 times 10 to the 8 meters. Hopefully you got that first time. If not, hopefully when it was set up, you managed to get it from there. Let's do one more question. See if I can pause and attempt this one. So first of all, what we need to establish is this distance xy. So we've got a right angle triangle. So we've got r and two r's the hypotenuse, so we need to get the distance xy. So if we do 2r squared minus the r squared, that will give us our distance xy squared. So 2r squared is 4r squared minus r squared equals the distance that we want, so that would be 3r squared. So to get distance, we need to do the square root. So that distance xy is root 3 lots of r. So what we need to do next is, we know that the gravitational force is g m1 m2 over r squared. So for both of these positions, so the position that it's originally in and when they are nearest to each other, which would be there, by the way, a distance r away, g, m1 and m2 are the same. It's a constant. So what we can do is a bit of maths, where we say that the original force times the distance r squared, which is actually root 3 r squared, is equal to the force when it's closer, or gm1 m2 for when it's closer. So that would be the new force, force 2, times the distance it would be at, which is r squared. So we need to square this root 3, so we end up with f1 times 3. The r squareds will cancel, so we're left with 3 lots of f1 equals f2. So coincidentally, it shows that the new force, force 2, would be 3 times the original force. So the answer would be B. That is a very challenging question. So if you got that, well done. If not, hopefully you could follow the explanation and then you can attempt it again. So thanks for watching.